So the same, what'd you say? Sorry.
You have the same amount of material or something.
Going in and out of certain states.
Okay. So, but does equilibrium mean equal?
No. It means balanced.
Means balanced. Okay, so what's going in, the rate of what's going in is going to be the same as the rate that's coming out. So when we talk about equilibrium, what we talk about is we have our, white on white does not work.
White on white on white.
Whoa.
So if we have our reactants and we have our products and we have so many, we have our reactants here and then we have some products over here. What we'll see is that the amount of reactants being made is going to be, the rate that the reactants are made is the same as the rate of the products going back the other way. Okay, so this is where we see the double-headed arrow. However, I do my arrows like this. You might like to do your arrows that way, but that's what a double-headed arrow means. It means that these can go this way and this way. So we're making product and reactant back and forth, okay? And it's at this equal rate. Any questions on that? On what equilibrium is? Okay. So what we have is we have this equilibrium equation up here. So so you have your products and your reactants, and then you have your coefficients. So to write an equilibrium expression, the only things we care about in equilibrium expressions are aqueous solutions and gaseous solutions. Any solid or liquid does not go into our expression. Okay, and these are our equilibrium expressions. It is going to be product over reactant. And sorry about the K's, but big K is your equilibrium constant. Equilibrium constant. So big K. And when we're talking about equilibrium, we're talking about gases and we're talking about aqueous solutions. So we're going to be either talking about concentrations or pressures. So usually if you just see K by itself, you're going to assume that it's Kc, which is concentration. Kp is for pressure. So products always over reactants. This is where we can actually look into the equation, and some of you forgot this rule yesterday. We can look at the equation and we can take those coefficients and we can substitute those in as our superscript. Okay, so that's the power. So C is to the power of little c. D is to the power of little d. Okay, so those coefficients go straight in, and those are the powers that the concentration or the pressure is going to get multiplied by. And when you do pressures, again, pressures are in parentheses, and that would be usually the pressure of, say, oxygen, O2, raised to the power of whatever. And we can relate these things together by using PERV NERT, PV equals nRT. And we'll get into some of that too. So any questions about how to write the expression? So big K is always equal to products over reactants. So what this is telling me is that our equilibrium, so the rate of the products is the same, or is equal to the rate of the reactants. So yes. So big thing here is if K is greater than 1. What can we say about that? If K is greater than 1, then that means that the products are favored. If K is greater than 1, that means the products are favored. If K is less than 1, if I give you a K value and I say the K value is 0.001, you would be able to tell me that if K is less than 1, you would be able to tell me that the reactants are favored. Okay? So what do we say if K is equal to 1? Well, okay. These are at equilibrium. Any K is at equilibrium. So if K is equal to 1, that means that they are equally favored. Any questions on that? So what you're going to see in your homework is the following. You're going to see, something like this, and you're going to have something like this, and then we're going to see something like this. So which one is the reactant and which one's the product? Whose concentration is going down? The red or the blue? The red's concentration is going down. Then that means it's a reactant. The blue's concentration is going up. So that means it has to be a product. Looking at this graph, you can sit there and you can say, is it at the same rate? Do they look similar? Do they curve about the same time? Yes. So they are at the same rate. So for every one reactant, we have one product. And then at what point are we at equilibrium? It would be where you see that line even out. So whatever this time would be right here would be where you're at equilibrium. Okay? So if we had something where it looked like this, whereas something that looked like this, who's reacting, I would say looking at that we're getting the reactant is 2 times, leaving as much as one product is being made. So you can roughly look at that and see. Any questions on the graph portion? Okay. So let's solve for 1. First thing you need to do for any time you have an equilibrium problem is write the equilibrium expression. If I do not see the equilibrium expression, then I'm going to take points off. And that's exactly what they're going to do in the AP exam. If you do not put the expression, having the expression there is a point. So the following reaction is at equilibrium at a particular temperature. So particular temperature is really important to us because if you're at a different temperature, then your K value is going to change. Okay? So first of all, write your expression. So first thing we see are these are in brackets, and I have molarity. So this is going to be concentration. So Kc is going to be equal to my products over my reactants. So the concentration of HI to the second power over the concentration of H2 to the first power times the concentration of I2 to the first power. So that would be 1 point out of the question. Now we're ready to substitute in. So HI has a concentration of 0.30 squared over H2 is 0.012 times 0.15. So put that in your calculator and tell me what you get. To 2 sig figs. 50. How do we make 50 to 2 sig figs? 50 point.
Can we also do it in scientific?
You could also do it in scientific. You could say 50 and then the bar over the 0. Or you could say 5.0 times 10 to the first. So here's something you're going to love.
Thank God.
No units. So K equals 50.
So the little bar represents the sig fig.
I guess so. I learned that the other day.
I've never known. I mean, I know that it means that it's infinitely repeating that number, but.
So no units. Any questions on how to solve for, so always products over reactants. Okay, next slide. We're going to cross this out. This one uses a rice table, so we're not going to. Number 2, no. All right, so now we want to relate Kp to Kc. So concentration, how can concentration and how can pressure, how can they be related? How can I get, what's the common thing, or what? How can I get them to be related? The number of, not molecules, but the number of moles. So PV equals nRT, so the N can relate pressure and we can get pressure in molarity using PV equals nRT. So here, it wants to say, it says at 1100 Kelvin, another K pressure is equal to 0.25 for the reaction 2SO2 plus O2 and 2SO3, and that's a gas. Calculate K for this temperature. So it wants to calculate Kc at this temperature.
Don't we have to subtract, don't we have to change the temperature to Celsius?
No. Okay, so here is what we are going to use RT from here, and we're going to use N. So here is the equation, and you must memorize this because they do not give it to you. So K KP is equal to KC times R times T to the change in N. So how to remember this? Be politically correct to the power to the delta N. Politically correct to the delta N. Okay, R is the universal gas constant. And that is, we are not using the 8.314 because that is joules. We are going to use the 0.0821 liter times atmospheres over mole K. So now we're ready to solve. So KP is 0.25. We're looking for KC. R is 0.0821. To the temperature, which is 1100 K. To the delta N. So delta N is the change in moles. So this is the final number of moles minus the initial number of moles. So on my reactant side, how many moles of gas do I have? Add the coefficients. 3. On the product side, we have 2. So 2 minus 3 gives me negative 1 for my delta N. So solve for KC. He's so loud. Yes. Yes. If you would like a 0, I will do it. Anybody get KC? To 2 sig figs? Did you get 23? 23. Okay, so I'm going to let you guys in on a secret. If N equals 0, if N equals 0, then what? KP equals KC when N equals 0. So the first thing I would do is I would look and see what N is. Is N 0? If N 0, then there's no calculations you need to do. All you need to do is say KP equals KC because the moles of gas, change in moles of gas equals 0. So always check N first. N is the change in moles of gas, final minus initial. Everybody good with KP equals KC, RT, delta N? Okay, so then let's do some manipulations and then we are done. So we can manipulate K when we manipulate the equation. So let's look at this very first equation right here. There's our KC. What happens from here to here? What happened to the equation.
You just put it in its regular. All the same reactors.
They flip the equation, right? When they flip the equation, what we do is we take the inverse or the reciprocal of Kc. So if you flip the equation, then you take the reciprocal of Kc. Now what happened when they go from here down to here? What'd they do?
They just got it in like regards to each line.
Huh? They halved it. So they multiplied everything by 1/2. Which means now the subscripts become 1/2 and of what they were. Which would be the square root of the whole thing. Okay, so if they would have taken it and they multiplied it by 1/4, the subscripts, or the superscript, sorry, would become 1/4. Everybody okay with that? Okay. So next. Here, we can take two. We have A and B, and we have products over reactants, and we come up with KC1. And then we do the same thing with C to D, and we have the D over C. And what they do is they take these two equations here, and they add them to make that one big equation. Well, when they did that, what did they do with the KCs? They've now multiplying. So when we add equations together, we multiply the KCs. Does that make sense?
Are we going to be cases
Huh? I need him sitting back here so I hear him every time he asks a question. Because then every time I say, huh, he's like, never mind. All right, y'all ready to do some manipulations? All right, let's do some manipulations. All right, so let's look at this. We have equilibrium constants for the following reactions are determined at 550 degrees Celsius. Calculate K at the same temperature for the commercially important water-gas shift reaction. And this is, so what I like to do is kind of go here and I figure out what is my goal. So this is my goal equation. These two at the top, I have to manipulate them in some way where I can get that goal equation. So let's go to the very first one. What can we do with the very first one to make it, to help manipulate this to get our goal? Flip it. Okay, so let's just take that equation and flip it. So CO plus H2O, we get COO plus H2. So we flipped it, so what happens to our K1? So it's 1 over K, or 1 over 67. All right, what about Second equation. What do we need to do with it? I need CO2 as a product. So I think let's just leave it alone. Which means K2 gets left alone, and it is 490. So I'm going to go ahead and make sure that this equation works out. So the COs cross out, and is that it? Oh, the little cobalts cross out. And we are left with H2O plus CO produces H2 plus CO2.
Are we crossing those out because they're on both sides?
Yes, because they're on both sides of the equation. And we want to make sure that we got our ultimate goal.
I wasn't sure if it had to do with them being solids.
Nothing right now. So K3 is going to be 1 over 67 times 490. Yes. And we should get 7.3 as our KC. Everybody good with that? Last slide. All right, calculate the Kc for this reaction. If the Kc for this reaction is 1.3 times 10 to the 4th. So what happens from one to the other? When we go from here to here, what happened? It doubled. We multiplied by 2, right? So what do we need to do with our Kc? Not square root. Square, yeah, sorry. 1.3 times 10 to the 4th squared. (1.7 times 10 to the 8th equals Kc. And that is that. So you have homework, which is the A portion.